I am Mark, virtual teacher instructor at Egnatia Career College. Today we'll teach drainage, insulation, and concrete slabs, framing systems, columns, piers, and girders, floor framing, laying out walls and partitions. This is video number 4. Drainage, insulation, and concrete slabs. After completing this unit, you will be able to perform the following tasks. Locate and explain information for control of groundwater as shown on a set of drawings. Locate and describe subsurface insulation. Determine the dimensions of concrete slabs and the reinforcement to be used in concrete slabs. Drainage. After the foundation walls are erected and before the excavation outside the walls is backfilled, filled with earth to the finished grade line, footing drains, if indicated, must be installed. Footing drains are usually perforated plastic pipe placed around the footings in a bed of crushed stone. If the site has a natural slope, the footing drains can be run around the foundation wall to the lowest point, then away from the building to drain by gravity. In areas where there is no natural drainage, the drain is run to a dry well or municipal storm drain. Vapor barriers. Another technique often used to prevent groundwater from seeping through the foundation is coating the foundation wall with asphalt foundation coating. At this point, subsurface work outside the foundation wall is completed, but backfilling should not be done until the superstructure is framed. The weight and rigidity of the floor on the foundation wall help the wall to resist the pressure of the backfill. If the backfilling must be done before the framing, the foundation walls should be braced. To retard the flow of moisture from the earth through the concrete slab floor, the drawings may call for a layer of gravel over the entire area before the concrete is placed. A polyethylene vapor barrier is laid over the gravel under fill. The thickness of polyethylene sheeting is measured in mils. Insulation. In cold climates, it is desirable to insulate the foundation and concrete slab. This insulation is usually rigid plastic foam board placed against the foundation wall or laid over the gravel under fill. Rigid insulation under the floor may only be specified for the outer 2 feet of the slab. The heat of the building keeps the frost from penetrating more than 2 feet into the perimeter of the floor slab. Like all materials, concrete and masonry expand and contract slightly with changes in temperature. To allow for this slight expansion and contraction, the joint between the concrete slab and foundation wall should include a compressible expansion joint material. Expansion joints can be made from any compressible material such as neoprene or composition sheeting material. This expansion joint filler is as wide as the slab is thick and is simply placed against the foundation wall before the concrete is placed. Concrete slabs. When the house has a basement, the floor is a concrete slab on grade. The areas to be covered with concrete are indicated on the foundation plan or basement floor plan. This is usually done by an area not giving the thickness of the concrete slab and any reinforcing steel to be used. To help the concrete resist minor stresses, it is usually reinforced with welded wire mesh. Welded wire mesh is sometimes abbreviated WWM and sometimes WWF for welded wire fabric. Where the slab must support bearing walls or masonry partitions, it may be haunched. When floor drains are included or where water must be allowed to run off, the slab is pitched, sloped slightly. A note on the drawings indicates the amount of pitch. 1/4 inch per foot is common. When there is any possibility of confusion about which way the slab is to be pitched, bold arrows are drawn to show the direction in which the water will run. When floor drains or forms are set for pitched floors, it is necessary to find the total pitch of the slab. This is done by multiplying the pitch per foot by the number of feet over which the slab is pitched. For example, if the note on a concrete apron in front of a garage door indicates a pitch of 1/2 inch per foot and the apron is 4 feet wide, the total pitch is 2 inches. The proper elevation for the form at the outer edge of the apron is 2 inches less than the finished floor elevation. Slab-on-grade installations may require electrical raceways to be installed in or just below the concrete slab in the crushed or gravel fill. These installations must be made so that they do not reduce the structural integrity of the concrete slab. An oversized raceway in the concrete slab may cause the slab to crack and settle unevenly. An electrician should be present during concrete placement to observe and correct any damage to these electrical raceways. All underground utility systems must be coordinated prior to starting installation, especially in commercial and industrial buildings. The service entrance section may have up to 6 sub-distribution sections or panels located throughout the building. Electrical feeders are required from the electrical service entrance section to these sub-distribution sections or panels. This requires detailed coordination between the electrical installer and the other utility installers prior to starting the installation of the utility systems. The electrical installation must be laid out around the other utilities, with the other utility layouts normally having priority. The other utilities to be coordinated may include plumbing, fire sprinkler, heating and air conditioning, and specialty systems. This coordination must be done for both the underground and above-ground systems. Framing systems. After completing this unit, you will be able to identify each of the following types of framing on construction drawings: platform, balloon, post and beam. Energy saving. Platform framing. Platform framing, also called Western framing, is the type of framing used in most houses built in the last 70 years. It is called platform framing because as the floor is built at each level, it forms a platform on which to work while erecting the next level. A characteristic of platform framing is that all wall studs, the main framing members and walls, extend only the height of 1 story. Interior walls, called partitions, are the same as exterior walls. The bottoms of the studs are held in position by a bottom or sole plate. The tops of the studs are held in position by a top plate. Usually, a double top plate is overlapped at the corners to tie intersecting walls and partitions together. In some construction, the second top plate is not used. Instead, metal framing clips are used to tie intersecting walls together. Upper floors rest on the top plate of the walls beneath. The framing members of the upper floors or roof are positioned over the studs of the wall that supports them. Platform construction can be recognized on wall sections. Notice that the studs extend only from one floor to the next. Balloon framing. In balloon framing, the exterior wall studs are continuous from the foundation to the top of the wall. Floor framing at intermediate levels is supported by let-in ribbon boards. This is a board that fits into a notch in each joist and forms a support for the joists. Although balloon framing is not as widely used as it once was, some balloon framing techniques are still used for special framing situations. In both platform frame and balloon frame construction, the structural frame of the walls is covered with sheathing. Sheathing encloses the structure and, if a structural grade is used, prevents racking of the wall. Racking is the tendency of all the studs to move, as in a parallelogram, allowing the wall to collapse to the side. There are 2 ways to prevent racking. Plywood or other structural sheathing at the corners of the building prevents this movement. Also, diagonal braces can be attached to the wall framing at the corners to prevent racking. Post and beam framing. Platform framing and balloon framing are characterized by closely spaced, lightweight framing members. Post and beam framing uses heavier framing members spaced farther apart. These heavy timbers are joined or fastened with special hardware. Because post and beam framing uses fewer pieces of material, it can be erected more quickly. Also, although the framing members are large, they can range from 3 inches by 6 inches to 5 inches by 8 inches. Their wider spacing results in a savings of material. However, to span this wider spacing, floor and roof decking must be heavier. Post and beam framing is sometimes left exposed to create special architectural effects. Structural integrated panels, SIPs, are factory-built panels with an insulating core to which OSB is adhered to the exterior surface and usually gypsum board is adhered to the interior surface. Both the exterior and interior surfaces can be altered to suit the design of the building. Wiring and piping can be embedded in the foam core as the panel is manufactured. SIPs are custom designed for each particular application. SIPs are joined together with screws, splines, and glue to create a weathertight, well-insulated wall, roof, or floor. The advantages of SIPs are that they do not include the number of interior framing members that frame construction does, so they do a better job of thermal insulation. They result in a more weathertight building envelope. There is virtually no waste created at the job site, and construction is faster. The structural core of this house in your textbook packet uses posts and beams as shown in details. However, this is not purely post and beam construction. The posts are 3.5 square steel tubing, and the beams are LVL beams. These are properly called beams because they carry a load without continuous support from below. These beams are supported only in the beam pockets on the steel posts. In this house, the post and beam construction does not include exterior walls. In pure post and beam construction, the exterior walls have widely spaced posts, and the space between is filled in with non-load-bearing curtain walls. These curtain walls are merely panels that fill in the space between the structural elements, the posts. In areas where hurricanes and high tides are a threat, some houses are built as pole structures. Pole buildings are a variation of post and beam construction. Poles, which are treated to be insect and rot resistant, are set several feet in the ground and 8 to 12 feet apart. A band joist or header is then bolted to these poles. The floors, walls, and roof are framed within the pole structure. Pole buildings are strong, they resist severe winds. Pole construction allows buildings to be kept above damaging floodwaters. Metal framing. Light gauge metal framing is used extensively in commercial construction in places where the strength of structural steel or reinforced concrete is not required. Metal framing is also very popular in home building where termites and water damage are known to be problems. Light gauge steel framing uses studs and joists, the same as wood framing. Unlike wood framing, steel framing uses tracks and runners in place of bottom plates and top plates. The lighter, less expensive grades of metal framing are not as strong as wood, so they are used primarily for interior partitions in conjunction with other structural materials. Metal framing can be pre-assembled just as you would pre-assemble wood framing. The runner is fastened to the floor with router-actuated fasteners. The wallboard material is fastened to the metal studs using an electric screw gun with sheet metal screws. Subflooring material is fastened to the metal floor joist similarly with power-driven screws. The construction drawings and specifications will indicate the type of metal framing to be used. The gauge must be taken into consideration before using certain tools, stud punch, actuated tools, etc., and special mounting devices, box hangers, conduit brackets, etc. Where electrical non-metallic sheathed cable is installed through metal framing, a bushing or grommet must be installed prior to installing the cable. Advanced framing. Advanced framing is the name given by the APA, the Engineered Wood Association, for what was previously called Optimum Value Engineering or OVE. It is a system of 2x6 framing members spaced 24 inches on centers, in place of 2x4 spaced 16 inches on centers. Advanced framing also uses aligned framing members to provide greater strength, so that some members can be eliminated. When the roof trusses are aligned directly over the studs, it is not necessary to use a double top plate. In this system, second floor framing is aligned with first floor framing. When wall framing is done with 2x4 spaced 16 inches on centers, 9.4% of the wall is solid wood. Wood conducts heat out of the building. Only the space between the solid wood framing can be filled with insulation. By using 2x6 studs spaced 24 inches on centers, the area of solid wood is reduced to 6.25% of the wall. The amount of framing material is the same. Not only does this reduce the amount of wood exposed to the surface of the wall, but it also allows for more insulation. The area of exposed wood is further reduced by special corner construction. In conventional framing, 3 pieces are used to frame the corner of a wall. To reduce heat loss through the wall, only 2 pieces are used. The third piece, which normally provides a nailing surface for the interior drywall, is replaced by metal clips. In advanced framing, many of the doubled framing members around door and window openings can be eliminated. Special hangers are used to support the header above an opening. Many frame building are constructed using some of the elements of advanced framing, but not all of them. Notes on plans and details will describe these elements where they are to be used. Examination of the first floor plan and the detailed drawings of this house shows that the walls are framed for maximum efficiency. Several details indicate that the studs are 2x6 at 24 OC. This allows room for more insulation in the wall. Also notice that the house is sheathed with 3/4 inch insulation sheathing. Interior partitions do not need insulation, and so they are framed with 2x4. When installing non-metallic sheathed cable through wood wall studs and floor joists, the cable must be installed at least 1¼ inches from the nearest edge. Where this 1¼ inches cannot be met, a 1/16 inch thick metal plate must be installed to protect the cable from nails and screws, columns, piers, and girders. After completing this unit, you will be able to perform the following tasks. Locate columns and piers and describe each from drawings. Locate and describe the girders that support floor framing. Determine the lengths of columns and the heights of piers. The most common system of floor framing in light construction involves the use of joists and girders. Joists are parallel beams used in the floor framing. Usually buildings are too wide for continuous joists to span the full width. In this case, the joists are supported by one or more girders, beams, running the length of the building. The girder is supported at regular intervals by wood or metal posts or by masonry or concrete piers. An exception to the above system of girders and columns might be when the floor is framed with floor trusses. Floor trusses can often span a much greater distance without a supporting girder than can solid wood joists or I-joists. Columns and piers. Metal posts called pipe columns are the most common supports for girders. However, masonry or concrete piers may be specified. The locations of columns, posts, or piers are given by dimensions to their center lines. When metal or wooden posts are indicated, the only description may be a note on the foundation plan. This note may give the size and material of the posts only, or it may also specify the kind of bearing plates to be used at the top and bottom of the post. A bearing plate is a steel plate that provides a flat surface at the top or bottom of the column or post. If the girder is supported by masonry or concrete piers, a special detail may be included to give dimensions and reinforcement details. Girders. Before the total length of the columns or height of the piers can be calculated, it is necessary to determine the size of the girder and its relationship to the floor joist. 3 types of girders are commonly used in residential construction. Steel beams are often used where strength is a critical factor. Built-up wood girders are constructed on the site. These consist of 3 or more pieces of 2-inch lumber nailed together with staggered joints to form larger beams. Laminated veneer lumber, LVL, is also popular for use as girders. LVL is an engineered lumber product made by gluing layers of veneer together. These beams can be manufactured in almost any size. They are very strong because lumber defects can be eliminated and all the grain runs in the best possible direction. The girder in this figure is to be built up of 3 2x10s. Determining the heights of columns and piers. The length of the columns or height of the piers depends on how the joists will be attached to the girder. The floor joists may rest directly on top of the girder or may be butted against the girder so that the top surface of the floor joist is flush with the top surface of the girder. To find the height of the columns or piers, first determine the dimension from the basement floor to the finished first floor. Then subtract from this dimension the depth of the first floor, including all of the framing and the girder. Then add the distance from the top of the basement floor to the bottom of the column. The result equals the height of the column or pier. For example, the following shows the calculation of the height of the steel column. Floor framing. After completing this unit, you will be able to perform the following tasks. Describe the sill construction shown on a set of drawings. Identify the size, direction, and spacing of floor joists according to a set of drawings. Describe the floor framing around openings in a floor. Sill construction. Where the framing rests on concrete or masonry foundation walls, the piece in contact with the foundation is called the sill plate. The sill plate is the piece through which the anchor bolts pass to secure the floor to the foundation. To prevent the sill plate from coming in direct contact with the foundation, and to seal any small gaps, a sill sealer is included. This is a compressible, fibrous material that acts like a gasket in the sill construction. All lumber in contact with the foundation, including the sill plate, must be pressure treated, PT, with an approved chemical to prevent decay. The entire construction of the floor frame at the top of the foundation is called sill construction or the box sill. The box sill is made up of the sill sealer, sill plate, joist, and joist header or rim board. The sizes of materials are given on a wall section or sill detail. For areas where termites are present, a termite shield is included in the sill construction. A termite shield is a continuous metal shield that prevents termites from getting to the wood superstructure. Floor joists. Floor joists are the parallel framing members that make up most of the floor framing. Until recently, joists in residential construction were 2-inch framing lumber. However, recent advances in the use of materials have produced several types of engineered joists. A common type of engineered wood joists is the I-joist, consisting of a top and bottom rib of solid wood and a thinner plywood web between the ribs. I-joists are often called TJIS because the first I-joists, introduced over 40 years ago, were named after the Truss Joist Institute, which developed the first I-joists. Although the materials in each type are different, their use is essentially the same. The joist header in each case is of similar material to the joist. When I-joists are used, the header is typically an engineered rim board that is manufactured to have the same depth as the I-joists. Notes on the floor plans indicate the size, direction, and spacing of the joists in the floor above. For example, notes on the foundation plan give the information for the first floor framing. When the arrangement of framing members is complicated, a framing plan may be included. On most framing plans, each member is represented by a single line. In the simplest building, all joists run in the same direction and are supported between the foundation walls by a single girder. However, irregularities in building shapes require that joists run in different directions. As the building design becomes more complex, more variations in floor framing are necessary. In a building such as the lake house, which has floors at varying levels, the joists are supported by a combination of girders, beams, and load-bearing walls. Lake house floor framing. The floor framing for the lake house is shown on Framing Plan 1-6 in your textbook packet. Notice that the framing plan is made up of a simplified floor plan and single lines to represent floor joists, beams, and joist headers. A more elaborate type of framing plan uses double lines to represent the thickness of each member. The framing plan shows the location and direction of framing members, but for more detail, it will be necessary to refer to Floor Plan 2-2 also. The floor framing in the lake house can be studied most easily if it is viewed as having 4 parts: the kitchen, bedroom number 1, bedroom number 2, and bathrooms, and the loft. There is no floor framing for the living room and dining room. These 2 areas form the heat sink for the passive solar features discussed in earlier units. The floors in these rooms are concrete to absorb and radiate solar heat. As each area is framed, the carpenter must identify the following: joist headers, locate the outer ends of joists. Bearing for inner ends of joists, beams, walls, etc. Size and type of framing materials. Length of joists. Spacing. Framing at openings. The joist headers are easily identified on the framing plan, but their exact position should be checked on the detail drawings. They may be set back to create a brick ledge, to accommodate wall finish, or to be flush with the foundation. The bearing support for the inner ends of some of the joists in the lake house is the structural steel and LVL beam core detail 5-6. This core consists of 4 1.5-inch square steel posts with LVL beams and steel channel beams. The positions of the posts are shown on all plan views of the house. The C8x11.5 steel acts as a beam to support the floor in bedroom number 2. The doubled smaller LVLs support the loft. The LVL beams form part of the roof framing. All of the LVL beams rest in beam pockets that are welded to the posts. The structural steel channel, C 8 x 11.5, is bolted directly to the posts. The inner ends of the remaining floor joists in the lake house are supported by bearing walls in the lower level. For example, some of the kitchen floor joists are supported by the west wall of the playroom, near the fireplace, and some by the LVL beam that spans the distance from the playroom wall to the foundation in the crawl space. The size and spacing of material to be used are given on the framing plan by a note. They can also be found on the wall section. Lengths of framing members are usually not included on framing plans. However, these lengths can be found easily by referring to the floor plan that shows the location of the walls or beams on which the joists rest. For example, refer to figures and find the length of the floor joists in bedroom number 2 as follows. 1. The dimension from the outside of the north wall to the center line of the 3.5-inch steel post is 14 feet 1 inch. 2. The dimension from the center line of the 3.5-inch post is 2 inches, so the overall dimension of the bedroom floor is 14 feet 3 inches. 3. According to wall section 3-4, the rim board is flush with the north foundation wall, so subtract 1¼ inch, the thickness of the rim board, from each end. 4. 14 feet 3 inches minus 2 feet ½ inch. 1¼ inch at each end, equals 14 feet and ½ inch, the length of the joists. Some floor framing is cantilevered to create a seemingly unsupported deck. Cantilevered framing consists of joists that project beyond the bearing surface to create a wide overhang. This technique is used extensively for balconies, under bay windows, and for garrison-style houses. Framing at openings. Where stairs and chimneys pass through the floor frame, some of the joists must be cut out to form an opening. The ends of these joists are supported by headers made of 2 or more members. The full joists at the sides of the opening have to carry the extra load of the shortened joists and headers, so they are also doubled or tripled. The number of joists and headers required around openings of various sizes is spelled out in building codes and shown on framing plans. Laying out walls and partitions. After completing this unit, you will be able to perform the following tasks. Describe the layout of a house from its floor plans. Find specific dimensions given on floor plans. When the deck, framing and subfloor or concrete slab is completed, the framing carpenter lays out the location of walls and partitions. The size and location of each wall are indicated on the floor plans. Drawings 1-2 and 2-2 are the floor plans for the lake house. Of all the sheets in a set of construction drawings, the floor plans often contain the most information. Before looking for specific details on floor plans, it may help to mentally walk through the house. Start at the main entrance to the main floor and visualize each room as if you were walking through the house. Visualizing the layout of walls and partitions. The lowest floor with frame walls in the lake house is the basement. Start at the 6.0 by 6.8 sliding glass doors H in the southeast corner of the playroom. This large L-shaped room covers most of the basement floor. Some plans list overall dimensions for each room. The plans for the lake house give this information by conventional dimension lines only. Many of the dimensions of the lake house framing are referenced to the columns of the structural steel core. The faces of some of the walls are an inch or 2 from the center lines of the columns, but for the sake of visualizing the layout of the house, these centerline dimensions are close enough to develop a good mental picture of the layout. The north-south dimension of the playroom is 28 feet 3 inches. The east-west dimension of the north part of the playroom is 14 feet 1 inch. The section of the playroom with the fireplace is 13 feet 10 inches by 13 feet 10 inches. It may be helpful to notice the overall dimensions of each room as you visualize its shape and relationship to other rooms. It will be necessary to refer to these dimensions many more times. At the north end of the playroom is a small closet. South of the closet is a hall leading to the bathroom and utility room. The bathroom has a shower, water closet, toilet, and lavatory. Notice that although most interior partitions are 3.5 inches thick, the wall behind the water closet and lavatory is 5.5 inches thick. This thicker wall is called a plumbing wall. Its extra thickness allows room for plumbing. The purpose of the utility room beyond the bathroom is to house mechanical equipment such as the water heater, furnace or boiler, and water pump. In the southwest corner of the utility room is a small opening into the crawl space on the west side of the house. Walking back through the playroom to the stairs, you will see some interesting features. A broken line in this area indicates the edge of a floor above. These floors can be seen more easily on the first floor plan. Also notice the location of the fireplace, which will extend up through the upper floor. The L-shaped stairs lead up to the first floor. It is obvious that this is not a full story higher, because a callout indicates that there are only 5 risers. This can be seen more clearly in the sections on sheet 4 of this house in your textbook packet. The L-shaped stairs lead up to the living room. Against the west and south walls of the living room is a plywood platform or built-in bench. Another set of stairs in the northwest corner of the living room leads to the kitchen and dining room. These rooms are separated only by a peninsula of kitchen cabinets. The kitchen is separated from a hall by a freestanding closet and enclosure for the refrigerator and oven. This closet and enclosure cannot be recognized as freestanding, meaning they do not reach the ceiling, on the floor plan. However, this can be seen on section 2-4. On the north side of the kitchen is a door to the deck outside. The east side of the hall has a railing that continues up another set of stairs to the upper hall. Beyond this railing, the floor is open to the playroom below. Above the open area of the playroom is a loft that provides storage or extra sleeping space. Access to the loft is by a ladder in the upper hall. The loft is shown on a separate plan on sheet 4. The loft is suspended on 2 beams of 1 3/4 inch by 9.5 inch LVL. The north and south sides of the loft are enclosed by a wall 2 feet 6 inch high. The east and west ends have a railing. A door at the end of the upper hall opens into bedroom number 1. On the east side of this bedroom is a hall that leads past a large, 7 feet 1 inch by 5 feet 1 inch, closet to toilet number 1 in the northeast corner of the house. This toilet room has only a lavatory and water closet. A tub in the next room also serves toilet number 2 to the east. Toilet number 2 has a closet with shelves for linen storage. This toilet room can also be entered from the upper hall. The remaining room is bedroom number 2. The garage is attached to the house only by the wood deck and the roof. The garage is a rectangular building with 4-inch walls, an overhead door, and a walk-through door. Finding dimensions. When you understand the relationships of the rooms to one another, you are ready to look for more detailed information. Frame walls are dimensioned in one of 2 ways. Exterior walls are usually dimensioned to the face of the studs. Interior walls may be dimensioned either to the face of the studs or to their center lines. When walls are dimensioned to their center lines, 1/2 of the wall thickness must be subtracted to find the face of the studs. For example, in this picture, the end walls are 12 feet 4 inch on centers. However, the plates for the side walls are 12 feet and 1/2 inch long, 12 feet 4 inch minus 3.5 inch. The width of the studs equals 12 feet 1/2 inch. Dimensions are usually given in a continuous string where practical. Overall dimensions and major wall locations are given outside the view. Minor partitions and more detailed features are dimensioned either on or off the view, whichever is most practical. This house includes an angled wall. The length of such walls can be accurately found by trigonometry. However, the accuracy obtained by measuring with an architect's scale should be adequate for normal estimating. As each wall is laid out, the plates are cut to length, and the positions of all openings and intersecting walls are marked. The wall frame is usually assembled flat on the deck. Its position is marked on the deck with a chalk line, then the assembly is tipped up and slid into place. Commercial buildings may require a thicker wall, where the electrical service panel is flush mounted, and the panel box is deeper than the standard 3.5 inch wall. Many times, this thicker wall requirement is not shown on the floor plan or drawing details. The utilities that are to be stubbed up from a concrete floor slab into a wall are installed prior to floor slab concrete placement and, therefore, prior to the wall locations being determined by the framing contractor. The utility installer must be able to accurately predetermine the specific wall locations.